So, in the last class we started with the shallow enclosure and we wrote down the basic governing equations. We wrote down the scaling, that in the core parameter, in the core, which are the numbers which are the dimensionless variables. So, if you recall, u c was given by as u g beta h cube delta t by gamma L. So, that was the first one. Then V c was given divided by V divided by g beta h 4 delta t by gamma L square, okay, where x c, if you recall, was x by L, y c was y by h, and T c was given as T minus T cold divided by delta T, where delta T was basically T warm minus T cold. Okay. So, those were the normalizations that we had. So, you can reduce the equations that we had. This also we wrote, I am rewriting them once again. So, reduce the equations. Okay. So, u c by x c plus d v c by y c is equal to 0. So, that would be the continuity equation and the momentum equation. So, I am rewriting this just for the convenience, so that one can recap what happened last time. So, this is u c Okay. So, that was the momentum equation. Similarly, the energy equation. Okay. So, where your epsilon was basically h by L square, which is much less than 1. So, till this point we kind of did earlier also, right. So, based on this now what will be the type of solution that we can expect. So, what people did was that, so this is a smaller, so epsilon is a smaller quantity. So, the solution for u c, v c and t c, right. So, these are the three variables. Okay. So, we do what we do is basically we do a series expansion. Okay. We do a series expansion. Now, the series expansion is u c, v c, t c, it is like triplets, and then it is u c, v c, t c order 1, order 0, then u c, v c, t c 1 plus u c, v c, t c, okay, 2. So, this will be of the order of epsilon, this will be the order of epsilon square, okay. So, and this will be of the order 1, okay. So, this is like a series expansion in which the because this term is actually very small, okay, we can do a series expansion of this, okay. Now what we do is that we take this and we substitute it in our individual momentum energy and energy equation and solve them systematically. So, solve by substitution. Okay. So, solve by substitution. Now, so what we do is that we substitute, okay, and and then what we do, we gather all the terms which has got the same power of epsilon. Okay. So, we basically group the terms which has got the same power of epsilon, okay, and we set individually those terms as equal to 0. Okay. So, this is what we do. So, basically what we do is that the terms are the terms which are multiplied by same power epsilon, right, are grouped together Okay. So, we group the terms which are together. So, for example, if the power is epsilon to the power of k, we group all the terms which has got power of epsilon to the power of k. Okay. And so, we start with k equal to 0 and then we proceed up. Okay. This is how we gather the term sequentially. Okay. So, this procedure is also called the asymptotic procedure, okay, or the asymptotic expansion. Okay. So, basically we group terms with similar powers of epsilon and set them equal to 0. Okay. So, for each epsilon k, okay, we must solve a system of 3 equations. Okay. That means basically UC, VC, TC, K. Okay. So, we basically start with k equal to 0. Okay. So, this is the asymptotic expansion procedure. Okay. So, this is the asymptotic expansion procedure. Okay. So, based on this, after we solve, okay, we find that except for UC, VC, TC 0, except for this term. So, accepting this, all other terms which are of the order x has got the same analytical form. Okay. So, except this, all other terms with power k, okay, have same analytical form. Got it? Okay. So, UC YC is equal to K1 PC is obviously 0, this is the core part that we are actually looking at, right. So, TC XC YC K1 XC plus K2 plus K1 square H by L square RAH YC5 by 120 minus YC4 by 48 plus YC cube by 72. Okay. Got it? So, this will be the generic form, right. So, how would you do now? You have to determine this K1 and K2 from end solutions. This is, remember, the core solution, right. So, from the end solution we have to find out that what will be the form of K1 and K2. Okay. So, the net heat transfer can also be calculated. So, but before doing that, we can take a quick look at one of the important graphs. So, this is, for example, the graph for the velocity and the temperature profiles in the core region, okay, taken from reference 40 from Bejan's book. Okay. So, what you can see over here is that this is the velocity profile that you see, okay, and this is the corresponding temperature profile. Okay. So, the temperature and the velocity profiles are kind of plotted. Okay. So, the degree of so there are two things we can see, that the velocity profile and the degree of thermal stratification does not depend on which x you are looking at, so long as you are into the core region. Okay. So, it is largely independent of x. So, you can understand that if you are looking in the core region, it is not sensitive to which longitudinal location you are looking at, right. It is kind of consistent across all the both the velocity as well as the degree of thermal stratification. This is like the degree of thermal stratification, both are independent of the longitudinal position x. Okay. So, velocity and degree of thermal stratification okay, are not dependent on the longitudinal position of x, okay, on longitudinal position of x. Got it? So, you can see that the velocity profile shows that typical form, that there is a recirculation, right. So, you have the typical form, okay, it is going back and forth. The temperature profile shows this gradual kind of a stratification level from top to bottom, which is what you would normally expect, okay, but it is independent, which is an important thing to note over here. So, going back now, if we look at the heat transfer argument now, okay, so the net heat transfer from T warm to T cold, right. Okay. So, that is Q prime. Again, this is not very difficult. So, it is the same form as what we had in our earlier discussion. So, that is the form that we have. So, generally this should have a general result will be Nusselt number bar will be K1 plus K1 cube 362,880 H by L RAH square. Okay. So, the general solution, so this is the Nusselt number. So, you can see that the heat transfer rate depends on the core axial gradient. So, this is the axial gradient. Okay. Okay. So, this generalized formulation for the Nusselt number is actually shown in another result, which I will pull up right now. So, this is figure 5.11 again from reference 40, okay, where we show that these are the two these are the temperature profiles, where here of course x1 is the same as x by h. Please note this x1 is nothing but x by h. This has been done just for the purpose of normalization, nothing else, okay, and we normalize just by h, L by h, because of the shallowness of the enclosure to make the results kind of tractable. Okay. So, that is what we have done. Okay. So, in this particular thing, and I would write down the Nusselt number here just in case we forget, because we will spend just a little bit of time discussing this. H by L RAH square. So, that was the Nusselt number that we had. Now, if this value of Nusselt number, that is H by L square into RAH, right, this particular factor, as it increases, the thermal stratification of the core must be taken into consideration. That means the two temperature profiles that you see, okay, will actually have a divergence. Okay, they will actually have, there will be a little bit of a gap between the two. They won't actually overlap with each other, right. Okay. So, So, let me write this down also as h by L square RAH goes up, the thermal stratification of the core must be considered. Okay. So, the thermal stratification of the core must be considered. Okay. So, so in other words, okay, it essentially means that okay, you have a degree of thermal stratification between the upper wall and the lower wall, right. That is essentially what we mean, okay, and these are obviously the end effects, okay, close to the wall, right. So, you can see that there is a degree of thermal stratification between the lower and the upper wall, right, which is quite evident from this plot, right. Now, in the limit when this goes to 0, okay, the two walls are basically one and the same. So, there is no thermal stratification at all, right, between the top and the bottom wall. There is no thermal stratification of the core, but as it increases, okay, as the limit of the Rayleigh number, this h by L into Rayleigh number square increases, you do get a thermal stratification of the core that becomes very important. So, you cannot make them, okay, resemble like by a single quantity, right. So, however, but when we actually this happens, that means RAH into HL square approaches 0, okay, what we can have is that the Nusselt number can actually be represented in a much more, I mean, by a unique function, right. Okay. So, and not only that, the K1 and K2 kind of merges in such a way that there is no gradient as such between them. Okay. So, this is the main point that we wanted to kind of emphasize. Okay. And of course, now what you can do parallelly, which I am not going to do over here, you can solve for the end region. Now, end region can be solved, right. Okay. So, that is rather complicated and it does not really give you any more insights than what we already have, right. So, what we do is basically that you have to match the solution, okay, at the core coming from the end region also. So, that end region has to be now solved categorically, okay. So, for that there is the discussion in Bejan, which I urge you to take a quick look, but however, it is like not that important to do it over here and it can be left as a homework assignment. Okay. But in essence, we have covered the core region and we have shown that thermal stratification is important provided you have a high Rayleigh number and HL square at a higher value. Okay. So, that is the most important part of this particular argument. Okay. So, now let us look at, so this is the form of Nusselt number, we already established that. Okay. So, so there is a discussion in Bejan where you actually have a summary of all the results of the different types, like for example, tall enclosures, shallow enclosures, what Nusselt number to use, basically what form of the Nusselt number to use, okay, and figure 5.14 of Bejan actually shows some of those Nusselt numbers as well. So, let us see if I have it here, then okay, I do not have it here, but anyway, so that is kind of left as an exercise, okay, but that is more like a handbook approach. So, you can just if anybody needs to consult an handbook, any practicing engineer among the audience, if they want to use an handbook where they want to read out what Nusselt number correlations to use, say for example, for square enclosures, shallow enclosures, tall enclosures, okay, and in the different limits what you are supposed to use, then I think that is a good starting point. Okay, that graph is a good starting point. It has got lots of data, it has been compiled based on a lot of data. Okay. So, so now that we have done it, we have done this, let us look at some of the problem of partially divided enclosures. Okay. So, the topic is partially divided enclosures. Okay. So, partially divided enclosures, there will be a few of these kind of things, okay, which are kind of rather interesting and comes from a design engineer perspective, that what are these enclosures and how they can be actually used. But But in essence, okay, we will look at some of the interesting problems, okay, in such, and we will learn that just by using engineering analysis, just by using heuristic analysis, how you can actually treat and kind of draw what will be the kind of design for these enclosures. Okay. So, so there are some interesting issues which we will start here, and we will take it to the next class also. Like for example, if I give you an enclosure like this, okay. So, whatever I will mark as hatched, those sides will be kind of insulated, that means they will have that adiabatic condition. So, now if this is a room, right. So, and if I have suddenly a prop, and this is say adiabatic, okay, this particular thing, okay, this may be adiabatic, this may be adiabatic, and these are the walls which are basically positive plus delta t and minus delta t. Now, if somebody asks you that what will be the recirculation pattern in this, right. Now, you have to if you start doing the math out, then it is rather complex, right. But can we, through the scaling argument, so many things that we have learned, can we do something to answer this kind? And what about if we have another enclosure sitting here, right? I can have a third enclosure which can sit here, right. I can have another thing that can prop over here, right. So, actually rooms, halls that you design can have lots of these kind of enclosures. Okay. It could be many things, it could be ceilings, tops that are kind of coming down, it could be like kind of partitions that you have created in the room inadvertently, or just by design. Now, you need to know that whether those kind of designs are helpful in maintaining a proper recirculation in the room. Okay. So, otherwise we will see what happens if you are unable to maintain such recirculations. Okay. So, what happens, for example, here, this is another typical problem, okay, that you have one enclosure here, one enclosure here, like that, right. So, what will happen to those kind of rooms? Once again, this wall and this wall are open, the rest are all insulated, right. So, if somebody asks you to analyze these kind of problems, okay, then you first and foremost should know which design is good. Okay. So, the design, that design is good which gives you a lot of recirculation, right, which gives you that kind of natural circulation pattern. But if some designs may not be actually good at all, right, it might lead to what we call thermal stratification. So, we have to look into some of these designs. So, in the next class what we are going to do, we are going to start evolving some of these designs, okay, and we will try to see which enclosures are good, which enclosures are bad. Okay. So, in the next class we will just pick it up from here and just do a little bit more systematic study on this without going into a whole lot of math. Okay. So, that should be the whole idea, to kind of from an engineering perspective, how can we actually evolve such designs. Thank you.